So today we're going to talk about analysis of variance. Now, I'm just wondering, have you guys, are you familiar with ANOVAs? Have you done ANOVAs? Do you know what ANOVAs are? What can you share with me what you know about ANOVAs? What are they, and what do you do them for?
You can take a stab so that you can tear it apart.
Say that one more time. You can take a stab.
If you want to tear it apart.
If you want to tear it apart, take a stab, and I'll tear it apart. Kind of sounds like a pumpkin thing to say. Let's take a stab at that pumpkin and see if we can pull it apart.
I think you have to have a series of different independent variables and dependent variables so you can compare and contrast among them which ones are the strongest and the weakest.
So which ones are the strongest and the weakest, those different independent and dependent variables? Okay, that's a good start. Can we add to that conversation at all? Would you agree? Would you disagree? How about my friends at my table here? If you can help her answer, you can have one of those Kit Kat bars.
I didn't look at the sheets either.
Anything?
Yeah, I haven't done it for a while.
Haven't done it for a while? So
I have done it, but not recently, so I'm not up to speed on it all.
You're pretty close, actually. The key with an ANOVA that's a little bit incorrect, usually, and what we'll be learning about today, is one dependent variable. If it's more than one dependent variable, we have to do the male versions of ANOVAs. Do you know what the male versions of ANOVAs are? MANOVAs.
That much I know.
That was a statistical male joke.
Okay.
Did you like it?
Good. Very good.
Glad we have male representation in the room. We're not going to go into MANOVAs here. This is a basic statistical refresher, but you could do a MANOVA, and then they usually separate into univariate ANOVAs. Univariate meaning one dependent variable. So you do an ANOVA. Now, last week we learned about t-tests. What were the special conditions on the t-test situation? Actually, it wasn't last week. Has it been a few weeks?
Yep.
It's been a few weeks. A t-test, you have how many independent variables? One independent variable, and how many levels? You got it. Two. So when you do a t-test, you have one independent variable, and you have two levels. We talked about independent samples, male versus female. We talked about intervention design. Don't worry, we're just getting started with the bad jokes. How many have we already had? Like 3 bad jokes? You might not want to sit at her table. She was taking a stab. They were taking a stab at things, and I don't know. But you're probably safe. They seem friendly now. We've calmed them down. So the idea is, with a t-test, you have one independent variable and 2 levels. Many times in the world of research, we have more than 2 levels. So if you have more than 2 levels of one independent variable, you could do t-tests, but that's not the right way to do it. Instead, if we have more than 2 levels of an independent variable, we do a one-factor ANOVA. That's one independent variable and more than 2 levels. Many times that is called a one-way ANOVA. And of course then we have the Blondie song. One way or not. No. Do you remember that?
Mm-hmm.
Okay. I was going to put that in the email that I sent out with, but I figured it would be better verbally and inappropriate in an email. So, sorry, I'm a little punchy today. So the idea is you have a one-way ANOVA when you have more than when you have one independent variable and more than 2 levels. The other situation that was correctly pointed out is sometimes you have more than 1 independent variable. Let's say you're interested in the effects of, a drug and gender on how people respond to things. So drug might be one independent variable, gender would be another one. So many times you have 2-factor ANOVAs. And there's no good Blondie song on that, but I can promise you that's the case as well. So 2-factor ANOVAs can be done. So what I was hoping to do with you today, despite the fact that one of our studio participants brought their computer and have SPSS available, is we weren't going to run through all the SPSS on that because 1 factor and 2 factors takes a little bit of time. We were going to kind of review things not go through the SPSS details, but kind of talk about the issues and make sure you have a good understanding of what these are and how they basically work. And the place to start is the handout here. And basically for a one-factor ANOVA, the guy who made the one-factor ANOVA, when he first created it, actually we won't tell a joke here, his name is Fisher. So guess what he calls his statistic?
Fisher one-factor ANOVA, he named it
But
after
it's not an R, it's not a T, it's an
F.
It's an F, and we always like to tell students, please don't get an F on this. But we've already had enough bad jokes for 10 minutes here, so we don't need another one. So it's an F statistic that we do. And the big thing about the F statistic is we look at the variance between the groups versus the variance within the groups. Now, if you remember back to the t-test, what did we want to have happen for the t-test, for the numerator? If you had two groups and we did the two-group situation, did you want big differences between the two groups? We did. So for a t-test, we wanted big differences between the groups. That's the same thing, basically, as the f-test. We want the numerator, the variance between groups, to be large. And if you look at the pretty picture, I kind of drew the red line in there. Variance between groups reflects the difference between the group means. And so in this situation, I just created a simple situation. One group doesn't get a drug, the other group gets a drug. Maybe you're testing their memory. And the idea is you want to see if the difference between the groups is large. So the numerator reflects the difference between the groups. And that's the treatment. You want that to be large. The denominator. In a t-test, the denominator measures what? Error. It measures error. How do we want error to be?
Little.
Small. The variance within group measures the error within a group. If you look at the example here, for the people who got the drug or didn't get the drug, you'd want the group means to be different. But for the people who got the drug, you'd want all those to kind of be the same, the scores to be the same. So an F-test, you basically look at the variance between the groups over the variance within the groups. Does that make sense for everyone? Mm-hmm. Yeah, let me know if you have any questions. I've been teaching undergrads all day who have been yawning and looking confused. So, if I'm going too slow, if I'm going too fast, just give me...
Can I ask a question? And let me know if you want to defer it to later. But I would think that in a sense, there would be data sets where you could use either the ANOVA or a t-test.
Yeah.
Because they're similar.
Yes, this is one of those situations, because in this situation, you have one independent variable and two levels. So you could actually do either a t-test or an ANOVA here. The base point for starting, though, the ANOVA conversation is the simplest situation, which is two levels. If you had more than two levels, you couldn't, but you're exactly correct. If you had more than two levels, there'll be some other issues that we'll talk about a little bit later that we'll get into that. But yeah, this one you could do a t-test or an ANOVA.
So how would you choose?
It wouldn't matter. The results would be identical.
So you do the t-test because it's more simple?
Most people usually do a t-test. If you have one independent variable and two levels, and you did an ANOVA for that, most statisticians would say, why did you do an ANOVA for that? Why didn't you just do a t-test? They would assume that the person didn't know any better, and they didn't get it. I've seen publications, actually, where that's occurred. So, yeah, if you have one independent variable and two levels, you do a t-test is the basic idea. But this is the simplest situation. So let's actually talk about this a little bit. Let's say you do the statistics for this, and you're computing an F value. Let's say you get an F value, if you want to write for your notes, where the F value equals 1. F equals 1. Happy, sad?
No variance.
Well, no variance. You're close on that. It's not no variance. The variance between the groups is equal to what?
The variance within the group.
Within the groups. Is that a good thing?
just then random.
Yeah, then it's just
It means your error is
error.
equal to the treatment
Yeah.
effect.
And then you have error.
So
begin.
if F equals 1, that means the treatment effect you got, what you did to these people or what you did to a situation is equal to the error. So an F of 1 is a bad thing. It means you're not going to be significant. What happens if you get an F score less than 1?
How less?
Any score less than 1. If you get an F score less than 1, what does that mean? You have more what than what?
You have more
Error?
error.
Error than treatment effect. Is that ever a good thing?
No, that's never good.
No, we don't want that ever to happen. Does it happen all the time? Yeah, pretty much. So an F less than 1 is that going to be significant?
No.
No, and that's why when you get a score of an F score less than 1, you write F less than 1 non-significant. If you get an F score of 1, well, you never statistically compute something, you get F of 1, but F of 1 means equal, and will that be significant?
No.
Never. So what we really want is an F score much greater than 1. The larger our F score is, the better off we are. The larger our F score is, the better off we are. So is that working?
Mm-hmm.
Okay, I think, did I bring my glasses in with me? Pocket? Yep, got them in the pocket. The rental car. Because we're not driving that Caliber anymore. Oh, people on the recording don't know what I'm talking about. Had a little accident with the Caliber, driving a rental vehicle now. Okay, let's stop recording one at this point with that fine note.